Howdy and welcome back. So where we left off was we were talking about, okay, how do we encode integral numbers in memory? And we started out by our discussion with just a half byte of memory. So we had 4 bits to represent some sort of number. And we said this positional number system makes it awesomely easy to represent positive numbers just using straight binary encoding. So if we wanted to represent 11, we could go ahead and use all 4 bits to go ahead and encode the decimal value of 11 in binary as 1011. We wouldn't be restricted to using each bit, though we would have a finite number of bits available to us. If we consider the range, of what 4 bits can represent, if we're considering this unsigned and storing only positive values, would be 0, which would be 0, 0, 0, 0, 2, 1, 1, 1, 1, which is going to be, I guess, 11 plus 4, in this case, 15. Okay, this is great, but what if we also want to store negative numbers alongside the positive numbers? So one idea that you might have is sign magnitude notation. So this idea is simply to reserve the most significant bit, so that to the furthest of the to the left, as a sign bit. The idea is that if this bit is set to 1, we have a negative number. Otherwise, we have a positive number. So if we had our old friend from the previous slide, 1, 0, 1, 1. When using sign magnitude notation, this no longer encodes 11. Instead, this most significant bit is simply a sign bit. If that bit is set to 1, it's a negative number. If it is set to 0, it is a positive number. Where the value is actually stored, use something other than orange, I'll use Aggie maroon, is here. So notice that 1 bit is being used exclusively to communicate whether the number is positive or negative, which now means that using sign magnitude notation, the range of values that we could represent would be positive and negative 1, 1, 1, which is going to be 1 plus 2 plus 4, or in this case, 7 to negative 7. Okay. So how do we determine if the number stored in here is positive or negative? Well, first we need to determine the number. So in this case of here, we'd have 2 times 2, to the 0. Let me just write the binary digit first. 1 times 2 to the 0 plus 1 times 2 to the 1 plus 0 times 2 to the 2. And notice in this computation, we are not using that most significant bit. Again, it is there. So adding this all together, we're going to get 3. And then the next kind of step in this process is to go ahead and look and see if that sign bit is set. In this case, it is. So guess what? We have negative 3. So this all looks good. It seems simple, to the point, straightforward, but we don't use this. And the question is why? Well, this method proves problematic with basic arithmetic. If in this case, we're adding, assuming that the binary values here are encoded, binary integer values here are encoded using sign magnitude notation, we have 3 and we have negative 3. And when we add them together, we get negative 6, because this here is going to be 4 plus 2 plus 0. So that's 6. And then we look at this sign bit, and that's negative 6. And well, this is a result that mathematicians would consider very wrong. In addition to this kind of additional issues with this encoding scheme is that now we have positive and negative 0 values. So if the sign bit is set and we have all zeros in the all of the bits to the right of the most significant bit, well, in that case, we have negative 0. If the most significant bit is not set and it is 0, well, in that case, we have, I guess you could say, positive 0 in this case. Anyhow, we have two different encodings for 0. So let's go ahead and get into a second idea, which is going to make the math more friendly to the math that you're so familiar with.